Why can't we fly a plane into space? What stops it from just flying higher and higher until it's in space? Well, there are several issues, but assuming we are in something like a normal jet airliner, then one of the main problems is the air, or the lack of it as we get closer to space. A plane flies because as it is propelled forward, the wings, which are shaped to make the air flow faster over the top of them rather than the bottom, generate lift. As the plane goes faster, the wings create more lift, and when the lift is greater than the weight of the plane, it will climb into the air. As our plane climbs higher and higher into the atmosphere, the air becomes less and less dense, so the plane has to fly faster to create more lift, until eventually it reaches an altitude where the engines either cease to function correctly because of a lack of oxygen, or the air is too thin to create enough lift. Just as we need air to breathe, then the engines need oxygen to burn to create thrust to propel the plane forward. Jet engines, however, can work at higher altitudes than people. We humans have a limit of about 8,000 metres or 26,000 feet, above which is what climbers call the death zone. This is where there is not enough oxygen for humans to survive for sustained periods. The summit of Mount Everest is 29,000 feet high, and the air density there is about 33% of that at sea level. This means that with each breath you take, you're only getting 33% of the oxygen. If you were to stay at this altitude without additional oxygen, you would suffer from a condition called hypoxia, where due to the lack of oxygen, the body starts to slowly shut down and die. At 12,000 metres or 40,000 feet, which is the upper limit for most modern airliners, the air density is about 18% of that at sea level. If you were in a plane that had a rapid decompression at 40,000 feet, you would have about 5, maybe 10 seconds to get your emergency oxygen mask on before you became unconscious. The highest flying jet plane in level flight was the Lockheed SR-71 Blackbird, with a height of 85,069 feet or 25,929 metres, and where the air density is just 2% of that at sea level. At that height, it was travelling at Mach 3.2 or 2,190 miles an hour. The SR-71 pilots had to wear a full pressure suit with its own oxygen supply in case of a cockpit decompression or an emergency ejection. This was put to the test when in 1966 an SR-71 piloted by Bill Weaver disintegrated at Mach 3.1 at an altitude of 78,000 feet, as it was performing a test flight to ironically optimise its performance. At that altitude, your blood will boil in a similar way to when you open a bottle of fizzy drink, as the nitrogen in your blood turns to gas in the low pressure atmosphere. The pressure suit worked and Weaver survived the descent from 78,000 feet, but tragically the navigator, Jim Zweyer, died of a broken neck as a result of the breakup of a plane. Now, while you would think that the SR-71 is fast, to get into space you need to reach what is called escape velocity. This is where you are travelling faster and gravity is pulling you back to Earth, and that speed is 25,020 miles an hour or 40,270 kilometers per hour. And if that wasn't a problem, there's also the recognised altitude at where space starts, at 328,000 feet or 100,000 metres, well over 3 times the highest flight of the SR-71. Normal jet engines like those in the SR-71 have a maximum airspeed limit of around about Mach 3.5 or 2,685 miles an hour. Beyond that, the air pressure and temperature becomes too high for the compressors in the engine to work effectively. For hypersonic speeds, experimental unmanned aircraft like the NASA X-43 use what's called a scramjet engine. The X-43 is currently the fastest free-flying air-breathing aircraft in the world, having flown at Mach 9.6 or 7,310 miles an hour in November of 2004. Scramjets do away with the turbine compressors of the jet engine, so they have no moving parts. Instead, they use shock waves in the engine to compress and raise the temperature of the air in the engine to burn the fuel and create thrust. And in theory, they could fly at up to Mach 20 and possibly beyond. The problem with this is that they won't work at speeds of less than around Mach 5, so they have to be brought up to speed by a rocket engine booster before they can operate, which is how the NASA X-43 worked. They also won't work in space because there is no air with oxygen in it to combust the fuel. So this is why space vehicles are launched by rockets. Rockets can have much more power and can operate from a speed of 0 on the launch pad to Mach 33 and beyond, which is the escape velocity of Earth. One of the earliest experimental space planes was the North American X-15, which reached a height of 353,000 feet or 107,000 meters in 1963 and was powered by a liquid rocket engine. But it had to be carried up to 45,000 feet, attached to the underside of a B-52 bomber before being released. Then of course we've had the Space Shuttle, the Soviet version of the Space Shuttle, the Buran, Spaceship One and the Boeing X-37, all of which were examples of space planes, but were really just rocket-powered gliders. Rockets differ from jet engines because they bring their own oxygen to burn the fuel and don't rely upon the atmospheric oxygen. This means that they work in space equally as well as in the atmosphere. The problem with rockets is that because they need to bring the oxidizer with them, it makes them very heavy. Look at the Space Shuttle for example. The external fuel and the tank to hold it, along with the two solid rocket boosters, weighed 1,940 metric tons at liftoff, and that's without the Space Shuttle, all of which has to be carried along with the shuttle to the edge of space where they are then jettisoned. The maximum payload the shuttle could deliver into a low Earth orbit was 27.5 metric tons, which, as a payload fraction, is just 1.3% of the total takeoff weight. Rockets, however, can create huge amounts of power, so they can achieve the speed that is needed to escape the pull of Earth's gravity and go into orbit and beyond. But what of the future? Will we ever get planes that can take off from an aircraft runway, fly into space and then return back to a runway? There are still considerable technical issues to overcome, but one design which looks promising is the Skylon. This is an SSTO or single stage to orbit design, meaning that unlike a rocket, it stays in one piece, rather than having a separate main booster stage which detaches and returns to Earth, and then a smaller second stage which then goes on into orbit. The key technology that makes the Skylon work are the Sabre or synergetic air-breathing rocket engines. Now these are a kind of hybrid jet rocket engine which can take off like a normal jet engine, breathe air up to 93,000 feet and at a speed of up to Mach 5.4, when it then switches to rocket mode and can fly into space for up to 800 kilometers or 500 miles above the Earth. It would then return to the Earth's atmosphere and then land as a normal air-breathing plane to be checked, refueled and then ready for another launch. Because it uses more efficient engines and the lift of the wings, it would use only 20% of the fuel compared to a conventional rocket. It would still need to bring its oxidizer for the rocket portion of the journey, but a lot less than would be required for a normal rocket. This allows for a larger payload when compared to the total weight of around 5.5% compared to the shuttle's 1.3. Unmanned flight tests of the Skylon could be happening by 2025, if all goes well. But a potentially large fly in the ointment is the recent advances in reusable rockets like the SpaceX Falcon F9R and the Blue Origin New Shepard. These could make the development costs of the Skylon look expensive for satellite deployment and supplying the International Space Station. One thing which could come out of it though is a rocket-less version of the Sabre engine, which could make hypersonic air travel more of a viable option than using a scramjet engine. Only time will tell, but this is an exciting time for both the future of air and space travel, so we may yet see a plane that can fly into space. So as always, thanks for watching, and please subscribe, rate and share.